In this lecture, we will start a completely new type of three-phase AC motor that is named as synchronous motor. At the very beginning of the lecture, we need to know why synchronous motor is called synchronous motor. As the name suggests, synchronous motor will have the capability of rotating with the synchronous speed. That means this type of motor will rotate with synchronous speed. What is synchronous speed? We know from our induction motor lectures. If we have a certain mechanical configuration, stator configuration, and we learn how that mechanical configuration looks like from our induction motor lectures. For a three-phase induction motor case, if we have that particular mechanical configuration, and if we give three-phase supply here, three-phase supply, after giving this supply, there will be creation of rotating magnetic field. The number of poles in the rotating magnetic field depends on the number of poles used per phase case. We know this concept from our previous knowledge. Now, for example, if we have 2 poles per phase, then there will be creation of rotating magnetic field north and south, which will have equal magnitude, that is 1.5 of peak amplitude of the sinusoidally changing magnetic field. And this magnetic field will be rotating in a certain direction, and this direction can be changed by changing any two connections of the three-phase supply. The speed of this rotating magnetic field is denoted as ns, which is named as synchronous speed, which is equal to 120 f, where f is the supply frequency over p. P is the number of poles per phase. And for induction motor case, we placed a rotor inside this hollow part, and we know that the speed of this rotor will be always less than the speed of the synchronously rotating magnetic field. For induction motor case, the rotary speed is unable to catch the speed of the rotating magnetic field. However, for synchronous motor case, we will have a certain configuration in a way so that this rotor will always run with the speed of synchronous speed. That means the rotary speed will be equal to ns. And for that purpose, the stator that we are going to use, that is exactly similar to our induction motor case. That's why I'm not going to repeat the stator configuration here. The only change will occur in the rotor side. For the synchronous motor, the rotor that is going to be used will have salient pole configuration, which will be supplied by an external DC source. So we are drawing the rotor using red color so that we can see the difference. This will have salient pole configuration, and as we are considering 2 pole per phase case, in the rotor side there will be 2 poles. This rotor will have a winding. This winding will be supplied by a DC source. So what will happen when this switch is on? A DC current will be flowing, and there will be creation of magnetic field on this bar, and that magnetic field will be static. That means if we consider south is being produced here and north is being produced here due to this DC supply. So when we'll provide three-phase supply, there will be a creation of rotating magnetic field which is virtual. We know this will have north pole and this will have south pole, and it will be moving, rotating, for this case in the clockwise direction. So this north side will be locked with this south side, and this south side will be locked with the north side of the rotor. If this rotor is placed on a bearing, so there will be bearing to hold this rotor, the rotor will start rotating with synchronous speed as this rotor is locked with the north pole and south pole of the stator rotating magnetic field. This is the operating principle in brief, but there are few more underlying physics which we need to know. Before I go for elaborate explanation, let me repeat how it operates. When we'll provide three-phase supply, there will be creation of rotating magnetic field. In the rotor side, by giving an external supply, we'll provide a DC supply. where the DC current will be flowing in this direction, and providing this DC supply is called excitation. When we'll say that increase the excitation, that means increase the DC current. This DC current can be increased either by reducing this resistance or by increasing this VDC supply. Now remember, the DC power from the external DC source to the rotor is given by means of slip rings and brushes. So if I draw the rotor part here using the red color, we have the rotor windings here. This is the rotor part, and this rotor will be placed on two bearings. One bearing will be here, another bearing will be here. There will be two slip rings, and we will connect two brushes, and here we need to provide the DC supply, and this DC supply will be supplied to the rotor winding side. We have rotor winding here, and this is the negative side, and this rotor will produce a north pole here and south pole here, which will be interlocked with the south pole and north pole of the rotating magnetic fields, and this rotor will start rotating with the synchronous speed. So this is the one of the techniques for supplying DC source or DC current to the rotor. Another approach is that a DC power supply will be mounted on the DC shaft, which is used to supply DC current to the rotor side. In that case, we do not need to use any brushes or slip rings. Just we need to place a rechargeable battery here, which will act as our DC source. And when we need to recharge the battery, just this battery will be taken out and the recharged battery will be placed for a smooth operation. So there are two techniques for providing DC supply to the rotor. One is supply from an external DC source. This requires brushes and slip rings. Brushes. Another technique is to supply from a special DC source that is mounted directly on the shaft. Here both the techniques have some advantages and disadvantages. For example, if we use brush and slip rings, we need to go for regular maintenance. We need to check whether these brushes are out of order or not, because we have frictional part here. So it requires regular maintenance. In addition, brush voltage drop can be the cause of significant power losses on machines with larger field currents. Despite these problems, this type of slip rings and brushes are used on all smaller synchronous machines, because to make the machines or motors cost effective. The process that is described here, that is supply from a special DC source mounted directly on the shaft. Now if we use permanent battery here, then it is required to recharge the battery very often. Another technique is that sometimes on larger generators and motors, brushless exciters are used to supply the DC field. An exciter that will produce DC supply when the rotor rotates from this three-phase supply is mounted, which will provide the DC source to the rotor. Next we'll see how to start a synchronous motor. Starting synchronous motors. Till now, we were considering the operating principle of this synchronous motor, considering the steady state condition. We considered the rotor was rotating with synchronous speed right from the beginning, and they were interlocked with the rotating magnetic field, and the rotor was having a constant speed. With this configuration, synchronous motor cannot be made self-starting. The fact that a synchronous motor has no starting torque can be easily explained. To understand the nature of the starting problem of a synchronous motor, let's see the operation of this motor right from the beginning. When we apply a three-phase supply, what happens? At that moment, rotor is stationary, but the rotating magnetic field starts rotating with the speed of synchronous speed. For example, if we have 2 pole per phase case and 50 Hz supply, then the speed of the rotating magnetic field will be 3000 rpm. So 3000 rpm. This is for a particular case. Now, the rotor was at a stationary condition and the rotating magnetic field is rotating with a speed of 3000 rpm. At the moment of the starting, suppose north pole is here and south pole of the rotor is here. So this rotating magnetic field will try to start the rotor in the clockwise direction. However, this rotor has very high inertia. So what will happen, as this rotating magnetic field is rotating very rapidly, before the rotor starts, the south pole will come here. When this south pole comes here, they will repel each other and the rotor will tend to move in the anti-clockwise direction. Before it starts moving in the anti-clockwise direction, again north pole comes in this position. Hence, the rotating magnetic field tries to pull the rotor in the clockwise direction. As a result, instead of starting of this rotor, the rotor starts jerking at this position. Neither it rotates in the clockwise direction nor it rotates in the anti-clockwise direction. And this happens due to high speed of the rotating magnetic field right from the beginning and high inertia of the rotor at the starting period of the synchronous motor. And that is why a synchronous motor cannot start by itself. Hence, in order to start a synchronous motor, we need to take some measures. Three basic approaches can be used to safely start a synchronous motor. Number one, reducing the speed of NS, that is synchronous speed. How can we reduce the speed of the synchronous speed? By reducing the supply frequency. In that case, though the process is a bit complicated because we need to change the supply frequency, but if we reduce the supply frequency, what will happen? The value of NS will be reduced. So the rotating magnetic field will be rotating with a reduced speed. So this reduction should be done in a way so that they can be interlocked easily with the rotor, and the rotor can start with slower value of rotating magnetic field. Then eventually we'll increase the supply frequency and come to our normal condition. So the speed will be increased gradually, which will not occur rapidly, and we can start our synchronous motor in this way. Another method is that we can use an external prime mover using an external prime mover to accelerate the synchronous motor up to synchronous speed. In this method, what we need to do, we need to connect an external prime mover which will start rotating this rotor by providing external force. So what will happen if the rotor initially starts moving with the synchronous speed, that is the rated synchronous speed. So when the relative speed between these two are reduced, even though we provide this supply, it will be very easier for them to be interlocked and move with synchronous speed right from the beginning. Finally, the method that is used for starting synchronous motors is using of damper windings. Using damper windings. This is the most popular method and widely used. How it operates? With this configuration, a squirrel cage configuration is added, for example like this way. We know the squirrel cage configuration. There will be bars, and by the end rings they will be short circuited in the both side, and we'll have this magnet in the rotor which will be excited by external DC source. Now, how it operates. The operation is very interesting. First of all, this DC connection is disconnected, and if we provide three-phase supply, what will happen? There will be a creation of rotating magnetic field, and as we have a squirrel cage configuration here, this rotor will start rotating in the direction of rotating magnetic field. So the rotor will start rotating with a speed near to the synchronous speed, not equal to the synchronous speed. As we know from our induction motor knowledge, this speed will be less than the synchronous speed. So when the speed goes near to the synchronous speed, the relative speed between this rotating magnetic field and the rotor speed will be very, very low. At that moment, if we give this DC supply, that means if we switch on this DC supply, the interlocking of north and south pole between the rotor and the rotating magnetic field will become very, very easy. So they will be interlocked easily. Once we connect this DC connection and they are interlocked, so they will start moving with the synchronous speed. When this rotor starts moving with the synchronous speed, then there is no relative speed between the rotor and the rotating magnetic field. So these rotor bars will not experience any magnetic field cutting, and no current will be flowing through these rotor bars. In this way, we can start a synchronous motor. In brief, if we want to start a synchronous motor using damper winding, we need to follow the following procedures. Number 1, disconnect the field windings. That means this DC source should be disconnected at the very beginning of the starting of this motor. Then apply 3-phase supply to the stator. So when we'll apply 3-phase supply to the stator, the motor will start running as induction motor. Under no load condition, this motor speed will be near to the synchronous speed but less than the synchronous speed. Once it gains that speed, then the third procedure is connect the DC power source that gives supply to the rotor. That means when we'll connect the DC source, at that moment the rotor is rotating with a speed near to the synchronous speed, and it will be easier for them to be interlocked, and the motor will start running with synchronous speed. These are the 3 procedures you need to remember when we want to start a synchronous motor. Remember, in the lab we are going to start this type of synchronous motor for different purposes. So when this type of motors will come, first of all, we need to make sure that this DC source is disconnected, then give 3-phase supply, motor will start running as induction motor. Then once it gains a certain speed, then we need to provide this DC supply. When we will provide this DC supply, the rotor will have north and south pole static magnetic field, and that static magnetic field will be interlocked with the rotating magnetic field, and the rotor will start rotating with synchronous speed. From the operation of this synchronous motor, it is evident that even though we increase the load in the shaft, as long as they are interconnected, the rotor will not change its speed, rather it will keep moving with synchronous speed. Now, if we keep increasing the load, as long as they are interconnected, it will keep moving with synchronous speed. Its speed will not be decreased, unlike induction motor case. Now, if we keep increasing the load, at one point, the rotor will be loaded in such a way it will become impossible for this rotating magnetic field to hold this opposite pole in the rotor side. So this interlocking will be disconnected and this rotating magnetic field will keep rotating, but rotor will come to the stop condition. So we can say for synchronous motor case, the motor will run either with synchronous speed or it will be stopped. The synchronous motor cannot run any speed in between 0 to synchronous speed. So the torque speed characteristics curve for synchronous motor will look like this. This is rotor speed and this point is the synchronous speed ns, and for synchronous motor this will have this pattern. If we have initial load is like this, the operating point will be here and this is the synchronous speed. This is tau r. If we increase the amount of load, so this point will come here, this is the increased amount of load and the operating point will be there, and this will fall on the same line, same vertical line, and the speed will remain same, and that is synchronous speed. Now the torque speed characteristics curve will look like this for induction motor case, as we know from our previous lectures. So when we'll start our motor with three-phase supply without providing the DC source, the motor will start running with this speed if we have this initial no load condition. Then once we connect this switch, this operating point will shift from here to here and motor will start running with synchronous speed. I hope it is clear to all of you. We'll continue in the next lecture. Thank you.